So let's look at this chemical reaction. I'm going to make water. To make water, I'm going to take hydrogen gas, extremely flammable by the way, mix it with oxygen, give it a little spark, and I'm going to make some water. Imagine hydrogen gas and oxygen gas are used in fuels in rocket ships. Okay, so you know when you're burning hydrogen gas, it's extremely exothermic. So this is going to be a negative delta H, a negative value. Okay, so this is very good. I'm going to put a happy face. It's nice to have, it's easier to give off energy than to take energy in, right? So there's a certain amount of energy there that was given off. But the problem is this. Look at the water and the H and the O2 and the H2O. What happens to the entropy in the system? Is it positive or negative? Okay, so you have 3 moles of gas, and you are turning into 2, so there's going to be more order as these molecules combine to make water. Since there's more order, the delta S is going to be negative. Negative delta S means it's becoming more ordered. If you remember the chart, S is here and it goes up from solid, liquid, gas, solid, liquid, gas. So if the change is going down, that means it's negative, it's bad. Okay, it's not as spontaneous per se. So I'm going to put a sad face here. Okay, so is this reaction going to happen? It's extremely exothermic, but it's not very entropic, meaning it's becoming ordered. So it's not very it might not be spontaneous. So what's happening here is if you want to know whether this reaction will occur or not spontaneously, you have to consider the battle between the entropy and the enthalpy and the entropy, okay? And that is given to you by a formula. The formula is called Gibbs free energy. Okay, so let me give you some, tell you first why they call it this. The Gibbs is after a scientist. Free energy means when you combine these two, you're able to determine how much energy you have extra to give to the universe, okay? So the formula looks like this, and the derivation will be given to you in another video. You don't have to know how it's derived at all. You just have to understand it, okay? So if you can see, they combine the enthalpy here and the entropy as well, okay? When you combine the enthalpy, we'll call this the enthalpy term, and the entropy term, you can tell whether a system will give you some free energy. Okay, so this free energy is the energy you get from a chemical reaction. It is free energy that can be used to do work if you wanted it to. Okay? And you have to consider both. You have to notice the units here. Delta H is, if you look at the thermodynamic chart, delta H has a unit of kilojoules per mole. Okay, so let me write that down. Kilojoules per mole. And delta S has a unit of J over mole K. J over mole K. So why do you think you have to put the temperature here? Yeah, because you have to multiply it by K so that the K here will cancel with this K. So you have Kj over mole, J over mole. You can convert this by dividing it by 1,000. You can get this to kilojoules per mole. You add these together, or subtract depending on what it is, and you get the free energy, which is going to be in kilojoules per mole. Which makes sense. Energy is in terms of joules or kilojoules. Moles depends on how much you have. If you have double the moles, you'll have double the energy. So now you understand what free energy you can get, the free energy you can get from the system to do work. From this reaction right here, for example. Okay? So let's see what happens What happens when you change the temperature? Is it good? Is it bad? Okay, let's see what happens. Okay, so there are two parts to this formula. Remember, the formula is delta G is equal to delta H minus T delta S. Okay, this is the enthalpy term, and this is the entropy term. And these two are battling each other. Whichever is, is better, it's going to win and give you more energy. I'll tell you what I mean. Okay, the temperature dependence of free energy comes from the entropy term. So the temperature is the temperature dependence comes from this entropy. You have to multiply that. Let me show you what I mean. Okay, so let's go ahead and do an example here. Delta G is equal to delta H minus T delta S. Okay, let's look at that example when we're making. Well, first let's see the scenario is the perfect scenario. Okay, let's say that we have something that is, first of all, let's remember, exothermic means negative delta H. Okay, you're giving off energy, so it's losing money, right? You're giving it away, so it's good because the energy of the reactants is going down to the products, and it's becoming more stable that way if this is energy, and it's giving off energy, so that's good. I'm going to put a happy face there. Okay, if it's endo, it's not so good because you have to put energy into the system. You have to make it a positive energy, so it's a sad face. Not good. I prefer the exo. Okay, and then if it's spontaneous, of course, it's going to be positive delta S. Okay, meaning it's more chaos. So that is going to be a happy face because that's the universe wants to be more chaotic. That's the second law of thermodynamics. And then if you have, I'm sorry, not spontaneous, it's called chaos, more chaotic. More chaotic, and a negative delta S means it's ordered, and it's a lot harder to, clean your room. For example, it's a lot harder to go from gas to turn into solid. Okay, it's not going to spontaneously go into solid. Okay, or become ordered. So remember those signs first. Okay, so let's go ahead and look at the happiest scenario. If delta H is exo, it is positive, right? No, I'm sorry, negative. That is a happy face. That's good. Okay, this minus here is this minus. I'm just rewriting it. The T is just, you're multiplying it. Okay, if it become more chaotic, then it is a positive. That's also happy face. Okay, so let's see what happens when everything is good and good. Okay, so negative minus a positive becomes negative. So it's always going to be a negative delta G. Okay, so every time you think of a negative delta G, you're going to smile because it is very exothermic, it becomes very chaotic, and the system wants to do that. A negative delta G means, oh yeah, that's going to be your free energy. That's the energy that you're going to be able to use to do work. Negative means it's giving it off. It's giving off free energy, so this is what you want. This is the best scenario ever. Okay, oops. Okay, let's look at a not so good scenario. Let's use pink, let's say. Okay, so the worst part would be if it were endothermic. That's so hard. I have to put work in, right? You have to put energy in. So that's positive. That's endothermic. If it becomes ordered, that's not very good. That's not very easy to organize things. So it's, remember, ordered is negative delta S. That's negative, and that's a sad face. Two sad faces. Okay, the negative sign here from the formula. Positive and negative makes positive. Your delta G is always going to be positive. So a positive delta G is very, very bad. That means there is nothing free, no free energy, no free energy. Okay, so this will tell us a little bit about our reaction. If there is free energy, this reaction will be spontaneous. That means it'll just happen on its own, not have to do any work, and it's actually going to give us work. If it's got no free energy, it is non-spontaneous. Okay, and of course there are going to be scenarios when one is better than the other. For example, like one's a happy face and one's a sad face. Okay, let's do another scenario. Let's make that red. Okay, so let's say it's endothermic. You have to put a lot of energy into it, okay? And it's a positive and it's a sad face. I don't want to put energy in, okay? Minus, let's say, even though it's endothermic, oh my gosh, it became very chaotic, right? So it has a lot of microstates. So that is positive delta S, and that is really good. Happy face. That's happy face. Okay, so if this value is hugely chaotic compared to a small positive here, this number might win. So this is called the entropy term, because a negative times a big positive number will give you a negative delta G. You see how it battles a little bit? But if this number is too big and this doesn't get too chaotic, then you might get a positive delta G. So the enthalpy and the entropy term are always in battle. Okay, we'll do the example in the next video because it might be a little bit long.